Okay, so yeah, I believe we're all set. So as Matthew said in his introduction, so I'm a faculty in the computer science department at Rutgers, and I direct the Intelligent Visual Interfaces Lab. So my lab's research lies at the intersection of artificial intelligence, visual computing, and human-computer interaction, with a mission to develop intelligent visual interfaces to empower digital content creation. So, with this mission in mind, um, I've been conducting research along four main research thrusts: developing computational models of human behavior, integrating these human centric building performance measures into the design and management of spaces, developing solutions to create free-form, immersive, interactive narrative experiences, and the use of serious games to study collective human behavior. So, in this talk, I will be primarily focusing on our research that lies at the intersection of architectural design and artificial intelligence towards developing solutions for intelligent, human aware building design. So, one of the main or major challenges that architects face is predicting and analyzing building human interactions at the design stage. So, this can be very complicated for architects due to the dynamic and context dependent nature of human behavior. So, how can we empower architects with this ability to predict the impact of a built environment on the behavior of its inhabitants? So, this is the key question that I seek to ask and hopefully answer over the course of this presentation. Current building information modeling tools provide only a static representation of human behavior. And while there exist mature techniques to simulate aspects of buildings like energy, its structural integrity, acoustics, wind, different lighting conditions, very little work exists which actually seeks to model the relationship between a building and its inhabitants. So these traditional design pipelines only support static analyses, which are agnostic to the dynamic behavior of its inhabitants. So the question that we seek to ask is, how can we represent buildings in use? Specifically, we wish to understand how human crowds actually inhabit space, which can then be used to support a richer form of analysis, allowing designers to fundamentally account for how people utilize a space during a building design process. So, sensors and crowd surveillance are sort of a de facto standard way to monitor the activity of people in a real indoor or outdoor environment. And these means they provide the ability to sense crowd behaviors in their most natural form. However, the data obtained is fundamentally limited, noisy, and interventions are simply not possible when passively observing crowds in the real world. Controlled laboratory experiments, which have sort of recently gained traction, offer an alternative solution. However, it is extremely challenging and expensive, often prohibitively so, to conduct these studies, and very limited interventions are possible in a laboratory setting. More fundamentally, while such solutions like sensing and laboratory experimentation can be used to monitor the activity of people in built environments, this approach fundamentally does not work for yet to be built environments, which is the focus of this talk. So we reframe our question. So how can we represent buildings in use prior to the realization? So virtual crowds offer a viable means to study buildings at the design stage. And while these techniques provide unlimited, noise free synthetic data, offering unlimited possible interventions, such as studying crowd evacuations in an extreme situation, current techniques lack fidelity and behavioral realism, which limit their applicability in applications such as design or planning. So this brings us to our first goal, which is to develop computational models of virtual crowds with an emphasis on behavioral fidelity and realism. So admittedly, there is a very rich body of work in the simulation of virtual crowds. However, these methods often make simplifying assumptions in the representation and control of virtual humans, which limits their applicability to visual effects applications. There is this important gap in crowds research which thus needs to be addressed. So in our work, we've been systematically addressing these limitations in traditional methods towards simulating realistic crowd behavior in novel, unseen environments and contexts. So I will sort of briefly provide a broad overview of our research in this topic, which investigates many aspects of crowd simulation, ranging from multimodal perception, planning-based control, to cognition, personality, and behavior. So as part of my PhD, I developed a synthetic vision model of how people perceive their surroundings by proposing a novel variable resolution egocentric field representation, which you can see in the illustrations on the slide. So this perception model serves as the basis for an affordance-centric control framework, enabling virtual agents to make human-like steering decisions when navigating in crowds. We then enhance this model with sound propagation, perception, and localization capabilities, allowing autonomous agents with the ability not only to see, but also to hear sounds in their surroundings and elicit appropriate behavioral responses to multimodal stimuli. We have challenged simplifying assumptions in how agents are traditionally represented and developed biomechanically grounded methods to model how bipeds plant their feet when navigating and avoiding collisions with neighboring agents in complex, crowded situations, such as that passageway example that you see in the video. In order to move beyond reactive and heuristic control policies, we've developed novel methods of real-time dynamic multi-agent planning, which rely on massive parallelization to scale to handle hundreds and thousands of agents in crowded situations. And developed planners which concurrently work in multiple problem domains by reusing planning efforts from coarser problem representations to help accelerate and refine computations in complex spatiotemporal domains. So this effectively allows us to simulate complex emergent crowd dynamics like the emergence of the vortex, which is shown in the image, which was not possible using previous established techniques. So recently, in collaboration with Professor Pavlovic and his team at Rutgers, we are investigating model-free techniques for simulating crowds, which don't make any underlying assumptions in how crowds are represented, and effectively capture the essence of real crowd observations while extrapolating to new and unseen situations. So this is very much an active, ongoing research project for which we were recently awarded support from NSF, and this will be a multi-year effort. So please stay tuned for more updates. So complementary to machine learning techniques, we are also looking at the conceptual underpinnings of how people fundamentally incorporate information from multiple contradictory information sources when navigating in complex environments. So these studies are critical and facilitate the development of cognitively grounded computational models of human behavior. So, our contributions include cognitively grounded models of signage, space, human memory, as well as the social influence that neighboring agents impose on our own wayfinding decisions. So, I'll just take a quick break, and may I request that everyone mute themselves to avoid any background noise? Okay, thank you. So moving on, so we've also looked at developing novel techniques to synthesize personality-rich virtual avatars. So our key insight here is to use Laban movement analysis as an intermediate representation of raw motion to help facilitate mappings with higher level parameters, such as the five-factor ocean personality model. So this effectively allows us to synthesize personality-rich motion in virtual avatars by controlling higher level intuitive parameters pertaining to a character's personality. And finally, we have integrated these findings into open source solutions and developed a graphical, accessible event-centric formalisms to facilitate the authoring and synthesis of complex multi-actor behavior. So while I unfortunately won't have the time to discuss each of these contributions in greater detail, in today's talk, I will sort of briefly highlight our work in the biomechanically based modeling of human crowds and how we can use this as the basis to help increase the repertoire of movement capabilities in autonomous virtual humans by analyzing how characters make contacts with rich environmental features. So as we discussed previously, current methods mostly rely on particle-based representations and reactive or heuristic control policies to simulate the aggregate dynamics of crowd behavior. So here's just a visual manifestation of these artifacts or limitations where particle-based representations produce live locks in narrow passageways, violate simple orientation constraints, and produce sliding in crowded situations. So the take-home message from this slide is that we as humans do not move this way. So to address these limitations, our work generates biomechanically plausible footstep trajectories for an agent to navigate in complex dynamic environments, providing a tighter coupling with locomotion and animation and producing more natural, human-like collision avoidance. So the key insight is to increase the complexity in the state and action representation of each individual to encode or represent footsteps, where individuals are not simply deciding where to go and how fast to go, but where exactly to plant their feet and how it influences the movement of its center of mass trajectory. So the movement of the character over the duration of a single footstep is defined as a 2D analytical approximation of the dynamics of an inverted spherical pendulum model using parabolas as shown in this image. And here we sort of turn to the wonderful body of research in bipedal robotics, which often model the movement of bipedal robots in a similar manner. So these piecewise parabolic curves are enough to capture the trajectories of a human center of mass by effectively varying its curvature, speed, and step size. So this allows us to efficiently and effectively search through the constrained space of permissible footsteps in order to make steering decisions while accounting for the constraints of human movement. So instead of relying on reactive or heuristic policies, we propose a real-time planner which synthesizes footstep trajectories for agents to reach their goal while avoiding collisions with other obstacles and moving agents. So a U-turn is an exemplary sort of example of the natural footsteps that our method generates. So the first step changes momentum towards the desired direction. However, because of the footstep orientation constraints, the second step cannot be oriented directly towards the target, and a third step is required to complete this change in orientation, allowing the character to sort of resume walking normally. So these dynamic collision representations, they allow these virtual characters to get significantly closer together. So characters can now sort of pack much closer together, allowing us to simulate more accurate egress simulations. And this is in sharp contrast to the particle-based models, where, as you can see in the video, these particle-based overlays are actually overlapping, producing these false positives of collisions, where in reality, these bipeds are actually able to safely and effectively congregate. So the characters that are simulated using our approach cooperate at doorways with human-like fluidity and precision. So this next doorway that you're about to see is so narrow that a single character can barely fit through it. And we will sort of see that the focused character in orange sort of takes a subtle sidestep towards the left, allowing the other character to go through. And this is in sharp contrast to particle-based models, which would have collided with the walls and slided before eventually squeezing through. So in spite of increasing this domain and control complexity by limiting the horizon of the space-time planner, effectively pruning the action space of permissible footsteps and amortizing the cost of computing of footsteps over several frames, a framework can still simulate hundreds and thousands of virtual characters that have this full bipedal representation at real-time rates. So next, let's look at how we can increase the motion capabilities of autonomous virtual humans by analyzing motion data to learn new motion skills and analyze the geometry of an environment to reason about its contact semantics. So I will go through each step in our proposed framework at a high level. So during an offline step, given a database of motion clips representing different motion skills for a character, we analyze each motion to define its motion signature, which characterizes the different contacts between the character's body parts, such as its hand and feet, and the environment during the motion, as well as the spatial constraints between successive pairs of contacts. So this is represented as a contact constraint graph, as you can see in the slide. So we also pre-compute a coarse collision volume of the character's motion during this movement, which we use for collision checking at a later step. Next, we analyze the geometry of an environment to automatically detect locations where motion skills may occur. So starting with raw environmental geometry, we consider its triangulated representation and cluster adjacent triangles with identical normals to define a set of surfaces. All surfaces that exhibit similar normal properties are then grouped together. So, given the motion signature, which has been computed by analyzing the motion skills in our motion database, and the processed environment geometry with the surface clusters that exhibit the same normal properties, the core thesis of our approach is to annotate regions in the environment where specific motion skills may be possible. So this is outlined in the algorithm that you see on the slide. So I won't go through this algorithm in detail, but at a high level, we can treat this as a constraint satisfaction problem, which we solve in an iterative fashion. So here's essentially a visual illustration of that algorithm in action. So we identify spatially co-located surfaces that satisfy constraints on the motion signature of a specific motion skill while avoiding collisions with any neighboring geometry, and determine the valid subregions on each surface where each contact in the motion may take place. So this annotated environment is then used to compute an extended or an enhanced navigation mesh with additional transitions or edges in the graph structure to indicate where this particular movement might occur. So we've also developed an anytime dynamic approach to dynamically repair these navigation mesh structures to incorporate changes in the environment geometry. So this extended navigation mesh can then be seamlessly plugged into existing navigation and animation systems, such as game engines. So to sort of allow us to animate fully autonomous virtual humans, which can now reason about their surroundings and rely on a richer set of dexterous movement capabilities when navigating in complex environments. So the case study in this video was to be able to synthesize a character with parkour skills. Okay, so these solutions that I have briefly described allow us to simulate high fidelity and realistic crowd behavior and make them an enabling technology for computer aided design applications. So we go back to our drawing board and we posit the use of synthetic models of crowd behavior, which can capture the essence of real observations while permitting extrapolation to new and unseen environmental conditions, as is the case during a design session. So this allows us to jointly capture the relationship between environment features and human crowd behavior. For crowd-aware environment analysis, which can then be used to effectively explore design spaces while accounting for human occupancy characteristics. So with these tools, we can now seamlessly simulate and visualize contextually meaningful behavior of how people might potentially act and interact in semantically rich spaces, like an office building shown in this example here. So the data obtained from these simulations can then be used to extract meaningful indicators of human-centric building performance, which can then be fed back to the designer and used to inform the design of the space. So these crowd-aware design solutions permit manual design exploration. However, it quickly becomes prohibitive to manually explore this high-dimensional space of environmental and crowd features. So to this end, we rely on automation to automatically analyze this high-dimensional environment and crowd parameter space, and automatically synthesize design alterations which can optimize designer-enforced criteria. So this offers this potential of a design loop where the designer is still firmly in control, but may leverage computational intelligence to help improve designs and account for non-intuitive factors related to human occupancy and behavior. So there are two main requirements for realizing such a framework. So first, we need the ability to efficiently and accurately predict measures of human-centric building performance without needing to run prohibitively expensive long-duration simulations. Second, we need to carefully consider how these measures can be integrated into well-established computer-aided design pipelines, while still preserving designer agency. So to handle this first requirement, we've developed a deep learning framework that allows us to instantly and accurately predict long-term crowd activity patterns. So crowd simulators make short-term movement predictions over small fixed time steps. Our goal is to predict long-term crowd activity, which manifests over extremely long time horizons while still minimizing prediction error. So our framework instantly predicts the entirety of a crowd simulation given the initial state. So given an image-based representation of the environment, the initial and desired final state of the crowd, we first adopt a lossless encoding and decoding strategy to support environments of any size and dimension within a fixed dimension deep learning framework. A modified SegNet neural architecture is then used to predict this long-term crowd activity. So the input to this model is a 3D tensor, which includes the initial and desired final states of the crowd, which are encoded in these image-based representations that you see here, as well as the topology or the geometry of the environment. The output is also an image-based representation. Oh, yeah. The output is, oh, sorry, I think I just jumped ahead. The output is an image-based representation of the crowd where the RGB value at each pixel denotes the average crowd flow at that location. So this value can be easily substituted by any other crowd spatial measure, which can be extracted from the raw trajectories that are generated from the simulated crowd. However, oh, there's an issue here. Oh, sorry. Yeah. However, by relying on this fixed dimension input representation, our framework cannot effectively handle and represent environments of any size and complexity. So to offset this limitation, we introduce two additional compression channels to help encode environments of any size into a fixed dimensional tensor. So we call this a cage representation. So the cage representation effectively compresses the A, G, and E channels. So these are the crowd initial state, the crowd desired final state, and the environment representation, while ensuring that the compressed input is consistent and preserves the navigability constraints of the original environment. So what I mean by that is that navigable cells in the original environment preserve their adjacency relationship in the compressed representation. So first in this process, for each, so we iterate through all navigable cells in the environment representation. For each of these cells, we compute the number of visible cells both along the X and the Y axis. Next, we group adjacent cells which share the same visibility values or same visibility properties. So these regions can now effectively be compressed into a single cell while still preserving the environment consistency property that I described previously. So for the A and E channels, the compressed value in the compressed representation is simply the average of the values in the uncompressed region. And for the G channel, we take the minimum value of all cells in the uncompressed region. So the 2D compression channel that is generated stores the reciprocal of the number of cells which were compressed independently along both axes, essentially encoding the size of the regions along both of these dimensions. And then these values can sufficiently be used to decode and reconstruct the original AGE channels from the compressed version. So during the decoding process, this compression tensor that I just described is used to decode the compressed output by copying the single cell value in the compressed image into the expanded cells in the uncompressed image. So in order to sort of evaluate the compression power of this cage representation, we compare the cage encoding and decoding scheme to several popular compression methods. So what we can see is that for axis-aligned environments, right, with purely rectangular corridors and rooms, the cage representation is guaranteed to provide a lossless compression in contrast to traditional image resampling methods. Cage is lossy when we have environments that have curved passages and non-axis aligned environments, but still exhibits reasonable accuracy. And I'll be showing some of those results later. So yeah, I was just looking at the chat. So David had a question. So what is the example of a crowd goal? So that's a great question. So in this particular study, we focus on crowd movement patterns. So a crowd goal in this context is simply a spatial region where individuals in the crowd are likely to be headed, right? So this could be an exit or any other location in the environment. And even though I glossed over the details here, the desired final state representation allows us to encode multiple goals within a compact image representation. So we can effectively specify that multiple agents within a larger crowd are likely dispersing in different directions. Okay, yeah, so I don't see any other questions, so I'll keep going. So given this pipeline, we have now effectively cast the problem of long-term crowd prediction as an image regression problem. And this allows us to leverage well-established neural architectures which have been designed specifically for this purpose. So in our experiments, we find that a modified version of the SegNet architecture is perfectly suitable for our purpose. We sort of honed in on this particular architecture as we find that it sort of preserves small object shapes and sort of helps retain boundary information such as narrow passages, exits, and doorways, which are critical for crowd activity prediction. And this particular architecture, in our experiments, we find it to be easier to train in an end-to-end fashion in comparison to other more fully connected convolutional architectures. So for training our models, we developed a synthetic data set of procedurally generated axis-aligned environments based on a floor plan taxonomy of 12 commonly found archetypes in modern architecture. We also curated a data set of real-world environments which were used purely for model testing. So for both the synthetic and real environments in our data set, we used a coverage-guided sampling method to generate a representative set of crowd contexts, so that is an initial and final crowd state, to help generate the A and G channels used in our pipeline. So to generate the ground truth, we generate accurate simulations using the technology and the method that I described previously, as well as a static approximation of crowd flow that was generated by essentially by doing like a static path analysis of the environment geometry. And then these two methods sort of provide a trade-off between accuracy in the ground truth and computation speed. So for our results that I'll describe, the model that we used was trained on a little over 7,000 samples using only the synthetic axis-aligned environments of a fixed size, so of size 112 by 112 pixels. So here, each pixel in the image denotes the size of a person, so of an agent, which in our experiments we set to 0.5 meters. A radius of diameter of 0.5 meters. So the input here illustrates the A, G, and E channels, which are overlaid on top of each other, right? So we can kind of see the topology of the environment. The red dots here indicate the distribution of the crowd, and the color gradient denotes the likelihood of where agents are headed. The ground truth is the crowd flow that was generated by running the simulations. The prediction is the crowd flow that was predicted by our model. And the prediction error is visualized as the signed difference between the ground truth or the simulated data and the prediction. So false negatives here appear in blue, and false positives show up as a red hue. So we evaluate the prediction accuracy of a model on a variety of benchmarks and crowd contexts, which were not seen in training. So the first benchmark uses a uniform distribution of the crowd, which are all moving towards the same destination. So this scenario effectively simulates an egress or an evacuation, where the entire crowd is exiting a building. The second benchmark uses a non-uniform distribution, where the crowd is sort of non-uniformly distributed in the environment, and the agents are dispersing in many different directions. So this is intended to simulate more everyday crowd activity. So we see that our model performs well on both of these benchmarks with minimal prediction error in comparison to the ground truth. So the third benchmark uses the corpus of real-world environments, which are non-axis aligned and include, as you can see, curved passageways. So even though our model was trained only on synthetic axis-aligned environments with rectangular rooms and corridors, we can see that it is still able to accurately predict crowd flow patterns in these more complex, realistic settings. So the model, which was trained only on a fixed size, 112 by 112 environment, was also tested on much larger environments. So the compression rate, or CR, that you can see on the left indicates the multiplication factor that was applied to the environment size. So a CR of 2 indicates an environment that was twice the size of the environment that the model had seen. So we can see that in spite of not having seen the larger environment settings, our model is still able to achieve very good prediction results. And this effectively highlights the performance of the cage encoding and decoding scheme. Okay, so moving on, maybe I'll just take a short water break, if that's okay. If anyone has a question or two, please feel free to let me know. Okay, all right, so let's continue. So moving on, right? So in order to tackle this issue of CAD integration, we've developed a system we refer to as DOME. So DOME is a user-in-the-loop method for interactively exploring optimal designs of environments which account for how humans use or utilize the space. At each design iteration, DOME analyzes the current design and produces a diverse set of design reconfigurations or alterations which sort of take into account different human performance indicators that the designer may have specified. The user can then interactively explore these design candidates and iterate to refine their original design. So it's important to note here that DOME does not replace, but it empowers or seeks to empower architects by deeply integrating within existing professional design pipelines. So here is a high-level overview of our framework. So starting with an initial design, DOME first analyzes how humans inhabit that space. By instantly predicting these crowd activity patterns, which can then be visualized and also used as the basis for a variety of spatial measures using the prediction framework that I described earlier. The user then parameterizes the environment design to encode structural integrity constraints like load-bearing walls, other constraints like wall clearance indicators, etc. And these parameters, design constraints, and spatial measures are used to formulate an optimization problem over the space of permissible environmental configurations. So a key requirement is to keep the user central to the design process, while using automation to provide not one, but multiple diverse suggestions to potentially help improving the current design. So to facilitate this, we first formulate our objective to include a weighted combination of a suite of spatial measures. So these measures can be generated from statically analyzing the geometry of the environment, as well as using dynamic human-centric building performance indicators, which are extracted from the crowd activity prediction models that I alluded to earlier. We also introduce a diversity term into this objective formulation, which essentially quantifies the Euclidean distance between the set of candidate solutions that the system returns. So the resulting multi-objective optimization formulation produces not a single, but a set of diverse yet equally optimal design alterations which maximize the aforementioned spatial measures while penalizing soft constraints encoded in G. So these include the clearance between walls, for example, while maximizing the diversity between the set of candidate solutions, subject to the constraints that the designer had imposed. So at a high level, what this formulation seeks to model is to provide a set of vastly diverse, so vastly different, yet optimal design reconfigurations of the original design that preserves the original intent of the designer while accounting for hard to interpret factors related to human occupancy and behavior that sort of manifests in a sort of a dynamic and long-term fashion. So instead of optimizing a weighted combination of these objectives, we instead treat each objective term separately. And we solve the resulting problem using a hierarchical multi-objective optimization framework that is shown in this algorithm. So I'll walk through this in a little more detail. So given an initial environment parameterization and a vector of objectives, so these include these building performance indicators as well as the diversity term, this algorithm returns a set of diverse yet optimal candidates for the user to explore and select from. At each iteration, we select one of these terms to optimize independently using an evolutionary algorithm, which is similar to CMA or the covariance matrix adaptation framework. And this is found to work well for non-convex optimization domains. At the end of each individual optimization iteration, a threshold constraint is generated. And then it is added to a growing vector of threshold constraints, denoted by T. So this threshold vector implicitly captures the environment parameters which were selected by the previous optimization iteration, and then effectively penalizes the deviation from these parameter values in subsequent iterations. So at the end of the main loop, the optimal parameter values are captured within this growing thresholding function vector, T. So the last objective, diversity, is optimized separately using an algorithm which is shown on the right, which effectively searches for a diverse set of near optimal solutions given the set of threshold functions that were constructed previously. So note that the other objectives are now effectively represented as penalty functions through this threshold vector. Okay, so this resulting diversity set is then sort of provided or fed back to the user who is then sort of able to systematically review each of the candidate designs, which are then used as the basis for subsequent alterations through a tightly coupled design and optimization process. So DOME effectively empowers designers to account for these difficult to interpret features of an environment with respect to its human occupants. So we perform a suite of quantitative experiments to evaluate the performance of DOME on both synthetic as well as real environments. So DOME is able to interactively generate optimal design solutions on each of these benchmarks and scales well with increase in size and complexity of the environment, with the GPU acceleration sort of providing an order of magnitude scale up in performance in comparison to the CPU implementation. So we also performed a series of studies, user studies, to evaluate the usability and usefulness of DOME as a system. So we compared DOME to two baseline interfaces. So the first one is a vanilla version of the Autodesk Revit software, which is a standard computer-aided design software used by architects, sometimes reluctantly. The second version uses DOME, so it uses the DOME plugin within Revit, but without the diversity term. So this system effectively returns only a single optimal design alteration back to the user. And the third version is our entire DOME system. So compared to the baseline interfaces, DOME is able to generate designs which are equally, if not more optimal, while still providing the ability for the designer to have the flexibility to explore from a wide set of diverse candidate solutions, thus preserving designer agency. So we performed a system usability study, which is a well-established study protocol to measure the usability of a system or an interface. And the study was performed with a cohort of architecture students who all had familiarity with the baseline Autodesk software on top of which DOME was developed. So the system usability score of DOME was found to be around 71, which is indicative of a usable and an accessible system. Finally, we also worked closely with a group of professional architects who participated in our study and used DOME in a free-form, unstructured fashion over an elongated period of time. And at the end of this process, they were all asked to fill out a survey. So from some of the questionnaire results, we can sort of gain insight that professionals in general find DOME to be a valuable addition to an established CAD pipeline, and state that it sort of helps them account for these human factors during a design process, which are otherwise limited to their own intuition. And they all sort of unanimously agree that that these human factors are an important ingredient which need to be considered within the design process. So here's an example case study where we use DOME to improve the general accessibility and the flow of an art gallery. So the videos on the right show users in virtual reality exploring both the default and optimized version of the space. We can see that the optimized gallery improves the general accessibility and the visibility of these exhibits from key vantage points as people move along the corridor. So we also performed a larger case study on a subway station in NYC. The result that you see here was obtained across several design iterations with professionals. But I'll just highlight the main changes that we noticed here. So the optimized design reduces the footprint of the kiosk, the information kiosk in the center of the subway, and changes the configuration of the stairwell in order to improve the bi-directional crowd flow in the subway. And we find in our simulation experiments that the flow patterns in the optimized version are significantly improved in comparison to the default version of the subway or the original version, especially when subject to high density crowded situations. So in some of our more recent work, we have also shown that the principles of intelligent human aware building design can also be utilized to configure other aspects of space beyond the placement of its walls. So for instance, we can also utilize such systems to help inform the placement of signage, to help people find their way in complex environments like shopping malls or train stations. So, so in this talk, I've described my group's research in intelligent, human-aware building design. So the research contributions that I've described in this talk are part of a much larger, constantly growing research framework, and have highlighted some of our contributions in this wider space. So specifically, we surveyed our work in simulating high fidelity, realistic virtual crowds, with key seminal contributions in perception, movement, wayfinding, as well as investigations into cognitive and data-driven modeling techniques. Our core approach has been to combine the benefits of model-based techniques, which are grounded in cognitively based experimentation, and use synergistic model-free representations to simulate high fidelity and realistic crowd behavior, to make it an enabling technology in other applications. Within the area of computer-aided design, we have made several key contributions in spatial analysis, the joint simulation of human building interactions, using machine learning to predict human building performance indicators, and how these measures can be used to inform the design of space. So beyond these contributions, we have also developed a multi-user virtual reality experimental platform that allows us to study collective human behavior. So these shared online living virtual environments offer the unique opportunity to combine the benefits of observing the interactions of real people in flexible virtual environments. I have also leveraged my research in virtual humans to serve as a stepping stone for research in embodied conversational avatars as well as interactive digital storytelling. So before I end my talk, I will very briefly review some of these contributions. So in the realm of storytelling, we have developed graphical interfaces and assistive technology to empower not just experts, but anyone and everyone to help create their own animated digital stories, which can be transformed from passive stories into immersive, interactive narrative experiences. We have looked into how natural language movie scripts can be automatically converted into 3D animated pre-visualizations. We've also looked into developing novel machine learning techniques for multi-modal storytelling to learn mappings and representations between natural language, images, and videos. In the realm of serious games, we've used platforms like Minecraft to study collective human behavior and developed a novel shared online living virtual environment to conduct crowd behavior studies. So such a platform enables us for the first time to combine the benefits of capturing and observing real human crowds in a scalable and efficient fashion through the flexibility of virtual reality. So in our studies, We have shown, for instance, how herding and imitation emerges when crowds are subject to immense stress when evacuating a building under fire. So this is illustrated in the image that you see on the slide. We've also used this platform as the basis for recreating past crowd disasters, like the 2010 Love Parade event in Freiburg, Germany, where many people unfortunately lost their lives due to a stampede. So our simulation and virtual reality experiments show how the stampede may have potentially been prevented by strategically managing the crowd and using sort of key spatial markers in the passageway where the stampede occurred. So all of this work that I have described in this talk are the efforts of the Intelligent Visual Interfaces group at Rutgers, without whom this work would have simply not been possible. My team regularly collaborates with academic partners all over the world to solicit their multidisciplinary expertise in areas including architecture and cognitive science to sort of further synergize our own expertise. We have also successfully engaged with industrial labs to gain insights into the practical ramifications of our research deliverables, which we regularly release as open source software that is widely adopted. Our research has been supported by NSF, DARPA, internal grants at Rutgers, and through generous gifts from our industrial partners. And finally, before I end, I want to extend my sincere gratitude to the Rutgers mentorship, only a few of whom are shown here. So their collaboration and advice has been invaluable during the early stages of my academic career, and I look forward to engaging with the wider Rutgers faculty in the years to come. So with that, I want to thank everyone for listening and hopefully learning, and would be happy to take any questions.
Thanks, Mubasir. We just let anyone at this point unmute your mic and ask us whatever you have in mind.
So I'm going to go ahead and stop the recording.